Our project is Gplay. It's a graph-based playlist continuation using neural collaborative filtering. Music is an integral part of our lives, and streaming services like Spotify have revolutionized how we consume music. However, with millions of songs and playlists available, it can be overwhelming to choose the right songs for a playlist. So that's where the optimization comes in. It's a process of selecting the best set of songs for a playlist. One popular approach to playlist optimization is collaborative filtering. It is a method to make recommendation by finding similarities in users' behavior. So in this project, we leverage graph neural networks to optimize Spotify playlist using this collaborative filtering. The question that we aim to answer is how efficiently and accurately LightGCN can recommend tracks for a playlist. So based on the learned embeddings, what kind of tracks are suitable recommendations to continue the playlist? So we have developed a filtering recommendation system that can recommend songs to a user based on the current playlist content and the song's relevance to the current playlist. And in this project, we have used this Spotify million playlist dataset, which is a public dataset containing 1 million playlists created by the Spotify users. It uh, it contains over 2 million tracks, and each playlist contains on average of 66 tracks. And each file in this dataset contains 1,000 playlists, and the entire dataset is of 40 GB of JSON files.
Hi, this is Ayush, and I'll be taking you through the data line pipeline of our project. So first of all we need to create a graph from the JSON file. For that, we're using graph tool. As graph tool is built on C++, it is very faster than other graph managing packages. After that, after when we create the graph, we need to take a subgraph of our main graph, as the main graph is too big to be trained by our limited resources. To do that, we select the largest component from the main graph. After that, since we want to use DeepSnap to generate our train, validation, and test data sets, we need to convert a graph to a DeepSnap graph, but the the graph is not compatible with the DeepSnap graph. So we need to convert it into a network X graph. And from network X to, we need to convert it to the DeepSnap graph. Coming to our model architecture, how does it look? So a model is basically a model will contain four layer of light GCN, and here you can see this class defines one single layer of the light GCN. And after we pass our nodes, all our nodes through four layers of GCN, we will get embeddings for all our nodes. And then what we do is we take dot product of a pair of nodes and pass it through a sigmoid function to get a value between 0 and 1. So once we get that, we pass a sigmoid value and the label for that pair of node to a loss function, which then try to predict the using that which our model tries to predict whether an edge will be there between two nodes or not. After so for evaluation, we have used the ROC AUC score, and as you can see here, our AUC scope on the test data set is of 0.89. And if I go down, you see how quickly the model is converging. That is to within 50 epoch. That just shows how simple and effective our light GCN model is. And this is what our AOC curves look like, which is a pretty good curve, indicating that the model is able to differentiate between positive and negative edges. We have also created a front end for this, where if you provide the front end with the playlist name, it will generate 10 songs for you using our model. And the end, these are the names of our project member, and these are their email IDs.